Hello. Hi, everyone. So I'd like to introduce myself first. I'm Ben Gidley. I'm the Director of Technology for Adetto. I'm a developer and architect by background, and we're here to talk to you today about trusting the browser.
Yeah, trusting the browser. Hi, I'm Tim Charman. I'm an architect at Adetto. I've worked for a very long time now. That doesn't really get you anywhere in this day and age, but my experience over the many years I've been working is mostly about integrating systems, and it's about working in areas like media, government, and now in payments, which is our main focus.
OK, so today we're going to talk about browser security and some of the new options emerging to secure code running in browsers. It's quite important because more and more people are moving towards serverless applications and also putting more and more smart logic in their websites. And what we find is it's very hard to secure that, and I think generally most developers are taught never trust what happens out in the browser. And we're going to talk today a bit about some of the ways you can secure things running out in a browser. So let's first explain what it looks like today.
Right, so the internet is a pretty good thing, I think. We all agree it's a good thing. It's been around for a while now. Things seem to be working OK. This is a model of the internet, typical model, where you have over this side a server, and you're protecting that server typically with things like firewalls, access control, that sort of stuff. Over on this side is your client running in a browser, and the browser is sandboxed, so you can run code there. The sandbox is going to try and protect the underlying computer from that code that is running. And talking in between the client and the server, you can talk over HTTPS, TLS, and that's going to protect the network communication between the two sides. That is how the internet works, right?
OK, but even with all this security, everybody is still taught to not touch the browser. And there's a whole number of reasons for that. So let's go for the first three of them.
OK, so here is a brick wall. This is meant to represent that on the browser, the user has full control of what's going on. They pick what kind of browser they're going to run. They may well download the code that you, as a developer, has written and run it in a way that you've tested. And that's great. But what happens then if the path that the user follows isn't the straightforward path, the path that's been tested? Or what happens if they start running their own code? Then you're going to see vulnerabilities appear, strange things appear, and you've really got no idea about what's going on there.
So even though you don't know what's going on, we often rely on TLS, and SSL as it's also called often, to protect our communications from the browser to the server. Now, most people think SLS, TLS is reasonably secure, and it is, but what they don't always understand is what it actually promises. So we go and look at a TLS website like the one I put up here. This is Adetto's website. And what we've got is we've got a certificate that says the connection is encrypted, and that means the connection is encrypted between the browser and potentially several people in the middle, actually, who the computer trusts. And that's very common on corporate networks or with antivirus software. There's often people intercepting your SSL. And only those people can intercept it. That's the first thing it says. It also says who you're talking to. It doesn't really say who you're talking to. It says that somebody, a certificate authority, has verified that the domain owner has approved the certificate. That's often very different from thinking of who you're talking to. If you go and look at SSL certificates, you'll often find them in the name of some weird company you've never heard of. And it's not always the person you're talking to. But then if we go and look at this the other way around, from the point of view of someone who writes a website, I put SSL on my website thinking I've secured my communications to the browser. What I've actually done is, all I really know is that potentially there's someone talking to me on SSL. I don't have any idea if the connection has been intercepted by someone, for good reasons or bad. I don't really have any idea whether the person on the other end is a human, a bot, a browser, a script, or something else entirely. There's no way for me to know that. And I have also no idea, especially if I'm using JavaScript and client-side code, which everybody does, whether it's actually running. It could easily be something someone else has assembled, and it could be doing something totally different. Now, there is one slight exception to that, which I should point out, which is something called two-way TLS. Now, two-way TLS is where you have a certificate on the browser side on the consumer's computer. That's almost never used in real life because it's too hard for consumers. Because the only way that works is if the consumer can keep those certificates safe, and the evidence, if we just look at the recent ransomware attacks around the world, people can't keep their computers safe. So that's the second reason why we don't trust the browser.
Yeah, so, and this is the third reason, right? Man in the middle. So a man-in-the-middle attack is where someone is going to sit in between the client who's doing their thing and the server and intercept the traffic, right? So we all know what that is. And there's a whole bunch of different ways that can happen. We've got a whole bunch of ways shown here on this side where the user is completely unaware that there's a vulnerability about to happen. The zero-day attack is a good example. The browser may have a vulnerability that nobody knows about. Or there's something that a user may do that makes the attack easy. And we can even talk a bit about when we were setting up this morning. We were setting up this morning, and here, which is really the place where a bunch of developers who are really savvy about security are sitting, connected to a Wi-Fi hotspot called Evil Hotspot. So I didn't use the standard Codemotion one like you meant to. They then went onto the internet, and even though it was popping up warnings saying, do you really want to go here, some of those users trusted the site and started doing HTTPS connections.
Yes. So there's someone in the buildings whose email we could have read this morning. We didn't, though, because we're not like, we don't do that kind of thing.
Yeah, we're the good guys. We don't do that. But if the guys here at conference are going to do it, then sure enough, the wider population who doesn't understand this, they're going to do it as well.
So, I mean, it's also worth saying, in the real world, this man-in-the-middle stuff is a real big problem. Google and Firefox recently commissioned some research where they looked at the Firefox auto-update mechanism, and that uses SSL. They found between 10 and 18% of everybody running Firefox Update was being man-in-the-middle by someone, which is an astoundingly large number to my mind. Most of those are probably harmless corporate proxies. So many companies intercept all your SSL traffic so they can read your Facebook and check you're not stealing their secrets. However, the security of that all depends on how well your company IT administrators keep that secure. And lots of companies don't, to be honest. The other one is antivirus software. Lots of antivirus software intercepts all your SSL traffic. Again, people don't often realize it does that, but that's how it checks for viruses on these things. And also some of it is hackers. Again, it's very common. If you go to, say, one of the hacker conferences, you'll find billions of fake Wi-Fi hotspots all trying to steal as much of your data as they can, because people find that quite funny. But it's worth just showing people quite how easy it is to intercept traffic on the network. So we've got a quick demo. Now, this demo might go horribly wrong because we just had to swap laptop right before this because the projector wasn't working. So we're not entirely sure it's working, but we shall see.
Yeah, let's see if the VM has rebooted.
It was. I think it's rebooted.
We think it's OK, yeah.
And the projector's now playing up again. OK, good. So imagine I'm a normal person. I've taken my Chromebook here. I've picked a Chromebook because generally people think Chromebooks are very secure laptops. They're designed by Google to be one of the most secure laptops there is. And that is true. There's nothing inherently wrong with Chromebooks. And imagine I've decided to go into a cyber cafe, and I've decided to go and buy a chair. So I go to a normal e-commerce site, and again, it's worth saying this e-commerce site has nothing wrong with it. It's something we've put together for this demo because, again, we don't like hacking real e-commerce sites. Amazon and people get grumpy about that. So I go into this site, and I decide to buy a chair. Now, here I am. I'm buying away. And if you notice, I've got a green bar at the top here. Everything's allegedly secure. Now, what's actually happened, though, is before I got to this point, I've managed to install a man-in-the-middle certificate on this laptop. Now, Tim had a slide up a minute ago as to the ways I could do it. So some of the most common ways are asking the user. So for example, I was visiting a company recently where their guest Wi-Fi network, it insisted you install a certificate to use the Wi-Fi. Another example is actually just at the start of this talk, one of the audio-visual guys came up to us and offered us a USB key to take a copy of our presentation. I've got a USB key back on our stand, which you plug it into any Windows 10 laptop and it will install a man-in-the-middle certificate. It's a special one. It actually pretends to be a keyboard, a mouse, and a network card and installs these things. You buy them on the internet. They're kind of script kiddie toys, very easy to use. There's lots of ways of doing this. So I decided to check out this chair. I fill in my details. I then continue. Yes, and then I'm going to fill in my credit card details. Now, credit card details are one of the big things people try and harvest off these things. So let me put in a fake credit card number.
That's surely not your card number, Ben.
No, probably not.
Okay.
Okay, and I've purchased my chair. All very exciting. Now, in the meantime, I'm playing the hacker. So, I'm going to capture your data. And let's switch over the screen, and hopefully this works. Yes, it turns out Mac Pros do not like the projectors here.
It's going to work, it's going to work, it's going to work, it's going to work.
Yes.
It sort of worked.
Okay.
Not sure what it's showing now.
Press escape.
Press escape, there you go.
Change to PowerPoint and press escape.
I think we have to swipe or... No. There we go. Sorry. So what we've got is what I've got. This is a little wireless access point that's used by people testing corporate networks and whatnot to see where the vulnerability is. No hacker could go online and buy this for like...
It's $99, yeah.
$99, yeah. Definitely don't do that because that would be illegal. And I'm sure no one here would want to do that. $99 online to you, no problem. Right. This wireless access point is providing a hotspot called Evil Hotspot or Evil Wi-Fi, and I've duped Ben into connecting to it. So so now we can see which one of these is it going to be, because we should have been watching.
It's a post.
Yes, it's definitely going to be a post.
Yep. Saturn.
There we go. And we've now captured at the bottom of the screen here, you can see where Ben lives is, well, wherever he lives. But the most important thing is I've got his credit card number, I've got his CVV, I can go and spend his money. And he didn't know. He didn't know.
Now, this is kind of emphasizing really why it's so challenging to trust the browser. Even the best existing security mechanisms everyone uses, like TLS, can actually be subverted by malware, by users doing the wrong thing, and so on. And the Firefox stat of 10 to 18% of people being intercepted is a really worrying number, because actually the next time we have a big security scare, it could easily be something like this. So
here's the thing, right? So with my hacker hat on, I say, well, then you can't really trust what's going on the browser, right? We've said people could be running code there, someone could be doing all sorts of bad things to you. And the data being transmitted can be intercepted, can be modified. Who knows what's going on? So the internet, maybe it's not such a good thing. Let's throw it away, and we're going to use paper.
So obviously that's a bit impractical, because the internet's kind of important these days. So what we're going to think about is what we could do to start preventing these kind of attacks. So one of the things we could do is if we could load some code into the browser and have some way of knowing it ran and be sure it ran. Also, and once we know it runs, we can add extra features in, like adding extra encryption and decryption so that even if someone's broken that TLS, they can't get your data. That would be potentially an interesting way of solving this problem, because then we'd know what's going on. And knowing what's going on is half the battle, because take, for example, if this was a bank, and this was a bank transfer we just shown, if I know someone's hacking their browser, I'm not going to let them move that $1,000. I'm simply just going to say no when they try and make the payment. And it's worth saying there's lots of banking malware doing this kind of tricks today. They wait till you log into your EOM banking, and as soon as you do a payment, they change the amount and they change the destination. And people often fall for this because they don't read the screens very carefully. So
here we go. Back with my skeptical hat on. Here is your browser. We've shown that you can run anything in the browser. We can intercept stuff. What are you going to do to secure the code that's running in the browser?
OK. So the first thing you think of doing is you say, let's put something in the middle. Let's call it a verifier. Let's imagine we know what code should be running in the browser because we put it on our website, didn't we? So if we signed that digitally and then checked it and asked the browser with, say, a security library to say, what code are you running, that would let us check it. Would that work?
Would that work? Well, I guess that would secure the code a bit, but I mean, we're talking about JavaScript here, right? I can read JavaScript. I mean, I'm not a JavaScript coder, but I can read JavaScript. So what's stopping me just having a really good look and working out what's going on and carrying on hacking?
OK, no, that's fair. OK, so why don't we obfuscate that JavaScript? So code obfuscation tools have been around for many, many years, and they actually do work. I mean, it's often said code obfuscation is a bit weak and you can break it, and there's definitely some code obfuscators are very weak. There's also some that are very strong. And if you use them well, you can get to a point where it's very hard for someone to read the code. Not impossible, but hard. That would probably stop you from doing that.
OK, so it's kind of hard. So I'm going to go after the communication between the client and the server. We've already shown how easy it is to go and intercept that. So what are you going to do about that?
OK, so yeah, you're right. There's a line in the middle. So maybe I've got obfuscated code sending messages, but you could spoof them. So OK, we'll encrypt those messages. Let's add some encryption on there. So now how do we encrypt something, though, from a browser? That's a bit of a challenge, because if I try and encrypt anything in the browser, you'll see me encrypting it. And thus, you can see all the data I'm about to send. So this is where we can use a technique called Whitebox cryptography. Whitebox cryptography is a technique where you take normal cryptography, take AES, and you design a version of AES to run where you know the bad guy can see the memory and can see the code, but they can't steal the key. This sounds a little bit like black magic. It's actually a very proven technique. You're probably all running devices right now in your pocket that are running Whitebox cryptography. It's just it's not very well advertised. Adetto have 5 billion devices in the world running this right now, as an example. Now, if we could run that over there in the browser, and we can come back to how that works in a bit, then we could encrypt these messages from the obfuscated code, and then you couldn't spoof them because you wouldn't know what's in them.
All right, so you solved the problem of me sitting in between there and seeing the code. It's double encrypted, right? So even if I strip the TLS, I can still see that it's encrypted with the special Whitebox crypto stuff. So I'm going to go back over here in the browser, right? Even if you obfuscate it as much as you like, I can read that code eventually. It might take me a week. It might take me a month. I'm still going to be able to get in there and work out what's going on.
Yeah, you're probably right. I mean, obfuscation is not perfect. I think there's actually mathematical proofs to prove it can't be perfect. But what if we make it a race? So a very simple thing you can do in any security thing is the goal is not to make something totally secure. The goal is to make it really hard and really time-consuming for someone to break it. I mean, that's how all cryptography works. We just make it hard that it takes billions of years to crack it in theory. So instead, we could add something called diversification in. Now, diversification is where you continually change the obfuscation and the keys, both structurally and numerically in terms of the keys, so that we keep changing it. Now, this concept works really well in a web page because I can make it so that every time you load the website, you get a different copy of that code, a different copy of the obfuscation, a different set of keys. So if you go and spend months hacking it, good for you. But by the time you've done it, that code and the version you're using is no longer valid. So essentially, I'm racing compute time versus human time. So is that enough?
Is that enough? Let's have a look. Well,
yes. Sorry, it's my turn, isn't it?
yeah, you have a go.
This is the problem with double act games. So what this ends up with is we end up with some idea on a server of what's going on out there in the browser. We actually can say, is your code running? And has it been tampered with? Now, that's interesting because back to my bank transaction example, if I know the code's been tampered with and someone's hacking it, I probably don't really want that bank transfer to go through because there is no good reason for you to be hacking your banking website while you're moving money around, probably. There's very few good reasons for that to happen. I can also make sure that even if you've got malware on your machine, they can't actually steal the data in transit. This is quite important because, again, that's one of the common attack vectors today. So potentially what we've achieved here is by mixing obfuscation, the diversity where we keep changing it, and the white boxes, we can change the security model to have some degree of trust in the browser and what's going on out there. It's worth saying this isn't absolute, but what it is it gives us some good flags and notes that we can use on the server to make some decisions. So it's probably worth just quickly drilling back into some of this stuff and just explaining a little bit more about it, because some of this stuff is a little bit weird. So let's go back to the white box stuff. I mean, the white box stuff does sound like black magic. It's worth saying this was invented in 2004 by a company called Cloakware, hence my T-shirt. And they're part of Adesso now, and basically it's a bunch of maths. And if anyone likes maths, you can go to bit.ly/whitebox tutorial, and it actually tells you how the maths works. If you don't like maths, I wouldn't recommend reading it, because it's quite a lot of maths. The end result of this is you can create an AES implementation by combining a key, a whitebox library, a seed, which is a random number we change for every time you use it, put it through a tool called a transcoder, and you get out a compiled blob of code in C or JavaScript that you can then use to do AES. And it doesn't expose the key. That's really useful because that gives us a route to secure things from. So the next thing we have to do is have some idea of what's running on the browser. So just as an example, imagine... Don't do that.
Don't do that.
You'd almost think these cards were in a very precise order. Imagine I didn't trust Tim here. And Tim is trying to fool me into thinking he's doing what I want him to do. So he's the browser. If I say to Tim, can you take 2 of those cards, please, and put them on the bottom?
Right. 2 cards, stick them on the bottom.
OK. Can you count 3 cards down?
1, 2, 3.
Take the next 2 cards and put them on the bottom.
OK, I'm going to put them on the bottom.
Then count the 4th card down from the top. And just tell me what it is.
1, 2, 3, 4.
And it should be a joker.
Right.
That works, thank goodness. So this is a really simple example. But what we can do in a computer program, imagine doing that logic between a browser and a server, doing lots of complex things. And it's entwined with the user data entry. It's entwined with the messages where the user's submitting a credit card number. So that it's in obfuscated code. So Tim here, if he wants to give me the right answers to my integrity verification challenge, if I go and ask the browser, what's at card 4, it's actually telling me what's in a DOM variable, what's in this bit of the Java code. It can only give me the right answer if he's actually been doing the work I want him to do, namely encrypting the data securely, making sure the integrity verification is running, making sure all the code signing's working, and so on. Now, again, what we showed there was a really simple version, but you can easily imagine in a computer program, you can do much more complicated scenarios, and it gets very, very hard for someone to second-guess you. You can also add in things like anti-replay, so that he can't just parrot a previous set of answers and so on. There's lots of ways to make this really challenging for him. We've lost a slide, Tim.
Well, that's not so good.
No. Let me just fix that.
We're just fixing something. Don't look.
Awesome. It's not here. OK.
Oh, we'll just talk about it.
So we'll talk about it. OK. Sorry, we had to change laptops just before, so we've got a slight glitch. OK, so diversity. So the diversity topic, Tim.
Right, so diversity is one of the main features of this, this system. And there's a lovely slide that you can't see that shows how we diversify something is by taking seeds and the source code and keys, and we're basically mixing it all up in a transcoder, code transcoder, spitting out obfuscated, secure JavaScript. So by taking that through the process once gives us one piece of diversified JavaScript. We're constantly doing this, so we can constantly push out diversified JavaScript, even to the point where every single time the JavaScript's downloaded, there's a unique version of that JavaScript. Yeah. So isn't it? Yeah. My cat talk. Imagine there's a picture of a cat. So the way I try to explain this is I've got a neighbor. This is a true story. My neighbor has a cat, and the cat is sick. And the problem with the cat is that the neighbor has to give it some medication every day, give it a pill. So the neighbor tries giving the cat the pill, and after one go, the cat's wise to this and spits out the pill. So the next day, the neighbor tries to grind up the pill and mix it in with the cat food. Well, a day later again, the cat knows that the cat food has got the pill in it and doesn't take the cat food. So then the next day, the neighbor has to wrap the pill in a bit of pate and kind of force it down the cat's throat. And this is what the vet said, right? I don't know about that being a nice thing to do to cats. But the point here is that while my neighbor is going to get stuck at some point, right? He's going to run out of ideas of ways of giving this pill to his cat. We can continually renew that code, and the cat or the hacker ends up with a continuous, an infinite job trying to solve this problem. And one of the key things here is that because we're serving a separately diversified piece of code every time, then the hacker may be sitting there working out what's going on, but in the end of the day, they just end up stealing their own credit card. You know, they can't steal any further than that. And
This is really what we're thinking you can now do with a browser. You can get to a point where by mixing together all these techniques, obfuscation, whitebox cryptography, diversity and changing, you can get to a point where actually we do a reasonable certainty. We know what code's running out there. We know the user's tampering with it or not. We know if they're debugging or not. We can tell if they've decided if it's a bot or not. And we can potentially stop those things talking to your APIs. I mean, bots, for example, are a menace to lots of sites where they go around and buy tickets and then resell them and that kind of thing. And by combining all these things together and interlocking them all, you can get a reasonably secure bit of code that makes it very difficult for someone to break it in a sane amount of time. And actually, most hackers will give up if they can't make money. And if you can stop them making money by breaking it in a sane amount of time, they'll stop messing with your sites. So it's probably worth just actually having a look at what that looks like in real life, because what we've just shown you there is, kind of a bit esoteric. So if I go back to my Chromebook and my shopping site. Now, previously, Tim there, oops, it's gone to sleep. That's not useful, is it? There we are. Okay. Previously, we were filling out a payment form, and I've just skipped straight to the payment form. And what I'm going to do now is I'm going to fill in my payment details again. Would work better if I didn't lean on the mouse pad. Okay, so here we go. This time I'll put an Amex card in. I'll use the same credit card number. And now this time I'm going to submit this data. This time this page is protected by all those things I just spoke about, actually. The JavaScript behind this page is obfuscated. And this JavaScript is set up to make it impossible for someone to intercept it. So you'll notice it's gone back across the thing. Oh dear, what happened there?
Yep, so I'm going to steal your connection again, as well as steal your data, haha, because I'm the hacker again, if you didn't work that out, right?
One of them didn't work. I don't know which one.
Yeah. So we get
I submitted it twice, you see. This page needs checking for that. Okay, there we are.
So yeah, now I'm the hacker, and as you can see, I've stripped the TLS type encryption, but we've still got the Whitebox encryption in place. So we're stopping the hacker from being able to, well, stopping me. Oh no, I can't hack anymore.
And it's worth saying, if I'd done, for example, if I'd opened that page up and opened developer tools, we'd have known about that too. There's all kinds of other things you can monitor with this sort of thing. If I then go and just show you what that page looks like, so if I open the page up, okay, so it's a normal website. It looks normal. And I go and open the secure page up. Okay, and I go and look at now, as soon as I click Inspect Element, it's worth saying, if I now try and submit a credit card, the person at the eShop's notified I'm actually debugging. Because you can tell when the Firefox inspector's open, for example.
Yeah, this is part of that multi-layered
Because it's
approach.
useful to know that. And if I had done this in a sensible way, I'd have had that open before I did this. And it's opened up an obfuscated JavaScript here, which is currently. And if I open that up in a tab, you can see there's some nicely obfuscated JavaScript there. Now, that is actually, I mean, again, people can have a look at this. This is on the web if you want to have a look at it. Feel free. It's very, very hard to understand what's going on in here. You'll see it's quite a long file with lots of tables of numbers, it would appear. And this is part of the features of making it secure. So, if I just quickly recap then, and go back to here. So, what we've just shown here is it working. And it's worth saying, if you wanted to use this solution, you could implement it yourselves. It's perfectly possible to implement protection like this. Or we also have a software as a security service. There's the shameless plug. I've got to get that in somewhere. And essentially, what we think we can do as a result of this is we think we have some certainty, as I said, that we know what's running out there on the browser. This is very useful for basically checking that someone isn't messing with your site, someone isn't a bot, and no one is intercepting your data. It's not perfect. It doesn't stop every possible exploit. For example, if someone's got a keylogger or if they're stood behind you watching you type your credit card in, this doesn't help. But what it does help with is it helps with a lot of those common scenarios. So are there any questions? There's someone with a microphone somewhere,
Yep.
I believe.
Hi. How mobile friendly is this?
It is mobile friendly. It works on mobiles. We have it deployed with a Russian e-commerce site, an eBay alike, essentially, who use mobile, who I think 60% of traffic is mobile. It does add size to the page. Security is never free. The files, we always ship gzipped, obviously. So the actual network load is about 170K extra, which is not trivial, but compared to an e-commerce site, it's not that much either. But it does work on all the mobile devices. It requires just a JavaScript, a browser that runs JavaScript. The actual code's ASM.js, so it's pretty light comparatively.
Okay.
Now, I mean, you wouldn't necessarily want to run this on a call that goes and gets the catalog, right? So anything that's publicly accessible, why would you, right? But
yes, it's true. That's true. You only run it on security critical calls. And it's worth saying, if it's a mobile app, this technology has existed on mobile apps for many years. It's relatively new on web in JavaScript. On the mobile apps, it runs on, again, most of you are probably running an app on your phone running this technology. So for example, in Holland, Ziggo's app runs essentially a variant of this. Any more questions?
Hi. What are the biggest drawbacks of this implementation? For instance, you cannot cache this kind of code, right?
You can. Okay, so yeah, you're right. You can. Well, you obviously remember the request we're protecting is a post, so you wouldn't be caching that anyhow. But the JavaScript code that we're protecting, you can cache a bit. So we don't actually need to give every single user a unique instance. What we need is a pool of instances. So I'll give you an example again. One of the sites we're working with, they've got about 10,000 instances live on their CDN at any point in time. So there is some caching, but it's more on a, and we randomly allocate, you get instance 1, you get instance 2, and you get instance 3, and so on. So there is some caching, but you're right, it does hinder caching to some degree. But again, it's also around the security critical calls. So it's about optimizing down to protecting login forms, credit card entry forms, moving money around forms, and not about protecting the homepage of your e-commerce site where you want to get that message straight in front of them to say bye, bye, bye.
Thank you.
Anyone else? OK, thanks. That's really it from us. So.
that's it from us. We're from Odetto. We have a stand over there where we can show this demo to you if you want to come and have a look,
Yes.
among other things.